Well, hello everyone. My name is Mark Hahn. I'm a sysadmin. Usually these presentations are given by the HPTCs, but I thought I would try to share some of the maybe lower level details of SharNET and how that might affect your jobs. This is the plan for my presentation. It's pretty simple. I think it's useful to remember that SharNET got to the way it is through some substantial history. We have clusters which are still operating after more than 8 years. That means that the technology they use spans many generations. The CPUs, the disk, the memory, the interconnect are all pretty varied. Some of the clusters are intentionally specialized. So for instance, we have GPU clusters. We also have contributed clusters, which are usually not very specialized in their hardware, but are specialized in how they handle scheduling. No two of the clusters are identical, unfortunately. They differ in pretty much every way possible. I think it's useful to be aware of the exact properties of the nodes you're asking to use when you submit a job. And I think it's a good idea to have at least a general grasp of what these parameters are. So for instance, on Requin, which is one of our oldest clusters, each core can do 2 double precision flops per cycle. The CPU clock rate is 2.6 gigahertz. So that's, 5.2 gigaflops per core per cycle. Sorry, per core per second. This is substantially different on both SAW and Orca. And we have a scattering of even more modern hardware, such as Haswell chips, where it's actually 16 double precision flops per cycle. Usually there's some trade-off between the performance of a node and the clocks. So for instance, it might be odd if you don't know about this, that Requin, our oldest cluster, actually has a higher clock than Orca, which is a newer cluster. And that really is just due to peculiarities in the bidding process when we buy them. There's something of a trade-off between the number of cores per node and the clock. So frequently, such as on Orca, we optimize for the number of cores in order to maximize the flops, even though the clock rate is somewhat lower. Often programs their performance is primarily determined by memory bandwidth. This is the case if you're doing any sort of large matrix operations, for instance. The question is really how quickly can the CPUs get to memory? Because for anything large, you'll be out of cache. Cache on a typical core is just in the megabytes range, whereas most people use memory that's in the hundreds of megabytes range, possibly thousands of megabytes. This table just describes the basic memory configuration for a range of clusters. I'll start again with the oldest one. Requin has the lowest total memory bandwidth, but because it only has 2 cores per node, its memory bandwidth per core is actually not that bad. So SAW is a cluster that's quite a bit nicer than Requin and newer, but it actually has less memory bandwidth per core just because of the way it's configured. I think this is useful to know because it affects your expectations about how fast programs will run on a particular cluster. And to some extent, it affects which clusters you intend to use. In general, there's been a trend towards higher bandwidth per core for newer machines. So you can see that Orca, which is a couple years newer than SAW, has better total bandwidth and also better bandwidth per core, even though it has 3 times as many cores per node. The last item I list there is Haswell. We have a number of Haswell nodes. No single cluster is all Haswell, at least none of the non-contributed clusters. The amount of bandwidth involved in one of these nodes is really quite remarkable, in the range of 120 gigabytes per second. So even for a 24-core node, that's a very large memory bandwidth per core. There are lots of programs that don't really care about this. So for instance, if your code has a relatively small memory footprint, or the memory footprint is very concentrated, you may have very high cache hit rate, and it may not really matter to you much what the memory bandwidth is. But again, if you're doing large, especially large matrix operations, it's something to keep in mind. It's also useful to remember that all modern machines are NUMA. SAW is something of an exception. It's sort of an older design that somehow snuck in. NUMA just means that memory is attached to particular die or particular sockets within the node. That means that there's some performance difference if your code happens to be running on a core which is not directly sort of close to the memory that your core is using. For the most part, this is something that you can't really optimize easily. The kernel just tries to do the right thing. But one interesting consequence is that if you're doing big memory serial jobs, it'll never be good. It'll be workable. So even though your memory is not local to the socket where your program is running, it's still pretty fast, but it'll never be ideal. And to me, this just speaks to the non-viability of people writing large memory serial codes. So ideally, you want to spread the memory around to where your program is running. And for the most part, that's approximated by memory per core, which is fairly standard across our clusters. It's in the range of 1 gigabyte per core. It's not completely uniform. So for instance, Orca has 1.3 gigabytes per core. SAW has 2. SQ-sub defaults in most cases to 1 gigabyte per core unless you request something different. I guess the reason I have that on there is if you're using about 1 gigabyte per core, you should be reasonably balanced. That's the take-home. If you're doing anything but serial or threaded, it's valuable to understand the node interconnect properties. And these properties can be characterized on multiple dimensions, but the simplest one is just bandwidth. So for instance, on Orca, which has QDR InfiniBand, the bandwidth that you should be able to achieve between two nodes is about 5 gigabytes per second. On SAW, it's about half that. It's an earlier generation of InfiniBand. And on this older cluster, it doesn't even use InfiniBand, it uses Quadrix, and its limit is about 1 gigabyte per second. Now, that's one of those things, sort of like memory bandwidth, that will matter to you depending on the type of program you're writing. So if you're sending a lot of big packets between MPI ranks, this matters a lot. If your packets are relatively small, then the second number is actually what matters. It's the latency. So these are the approximate user-measured numbers for these three clusters. The interesting thing is that the oldest cluster there, which has Quadrix, actually has a slightly lower latency than the other two clusters. Both SAW and Orca have an interconnect which is not fully connected, so every node doesn't have the same performance properties to every other node. And that's just because sets of nodes are plugged into a switch, and the switch then is uplinked through a network to other switches to reach other nodes. So some paths between SAW nodes are not as fully populated with bandwidth as others. Unfortunately, the scheduler doesn't provide strong controls for this, so it's not something that you can easily control for yourself. It's probably just something to keep in mind. That's also why I only quote one significant digit on the latency, because on SAW, for instance, if you're on the same switch, that is, you're on nodes that happen to be plugged into the same switch, the latency is actually comparable to Requin. It's about 1.4 or 1.5 microseconds. But if you're going between switches, the latency can be up to about 3 microseconds. Basically the same thing for Orca as well. There are a number of other clusters that also have InfiniBand, for instance, Monk and Angel, and possibly some others. They will generally have performance that's similar to Orca. We have a number of other clusters that don't have any special interconnect. They just have gigabit, and their performance for gigabit is much, much poorer than this. I should have put this on this table, but for gigabit, the bandwidth is at most 120 megabytes per second, and the latency will be about 40 microseconds. So you can expect roughly a 10 times slower interconnect performance on a gigabit cluster. So storage is often a problem on SharkNet. To us on the inside, it's never really clear whether that's because we provide bad storage or whether it's just complicated. So I'm going to try to explain some of the complication. The way we tend to think of storage performance as being a combination of two factors. One is metadata, which has to do with the structure of the files. So when there are many or small files, you know that the activity will be metadata intensive. Technically, any file creation, renaming, deletion, or stat listing operation is considered a metadata operation. So if you have code, for instance, that generates a whole bunch of small files, that is metadata intensive, and for most of our file systems, that will be slow. Basically, you can think of our file systems as having a fairly low maximum metadata operations per second, somewhere in the range of, let's say, 1,000 operations per second. So that if your program is doing a burst of 500 operations per second, you know, it's writing 500 small files in 1 second, you're basically consuming half that storage unit's metadata capacity. And that means other users won't be able to use it during that time. It's useful to know that when you type ls and you see a colorized output that cues you into what the types of your files are, or even a character after the file that indicates whether it's a directory or a link or something like that, that is expensive because ls is fetching details on the type of the file from the file server. And that's a metadata operation. You can avoid that by changing what ls does. So if ls does not present you file type information, it will run faster. And if necessary, we can show you how to do that. On some systems, I think this is actually the default. It might not be the default universally. And the reason I mention this is just because we often get tickets where people are saying, when I type ls, it's hanging. And what that really means is they happen to be in a directory which either has so many files or is on a file server that's slow, that it's taking a long time to fetch all that size and type information. As opposed to metadata, the other sort of axis parameterization of I/O is large streaming I/O. And most of our file systems are actually designed for this. So if you're writing fewer big files, that's what we consider large I/O. Writing the files does not create metadata operations, at least not in exactly the same way. So when you open a file and then write it and it's large, the only metadata operation there is opening the file and closing the file. All of the other operations go to a different server. Basically, Lustre systems are split up into one server which handles metadata operations and a number of other servers which handle the large file I/O operations. So the single metadata server is often a bottleneck. But if you're doing large I/O, that's often sort of randomly spread across these other file servers. Lustre is the file system that we use for that most times. When you're doing large I/O, you should aim to write blocks in terms of megabytes. This often means calling an auxiliary function in your programming language, in your library, to set the block size. So in Fortran, you can do this. In C, you can do this. I happen to know the C one in particular is set vbuff. If you're using stdio, you can do set vbuff, and it will buffer up to whatever size buffer you want. This can cause a huge improvement in the performance of your program. One sort of side consequence of this is if you are writing to the same file from multiple nodes, in most cases on Lustre, there will be a great deal of additional locking incurred by that. And the reason is that Lustre tries to present a very strict interpretation of file system semantics. So if you're appending to a file on one system and appending to the same file on another system, in order to do a write, the node will have to fetch the lock, perform the write, and then give up the lock to the other system. And moving locks between systems is relatively expensive. I guess you can think of it as a metadata operation in a sense. So I guess a good pattern for doing large I/O is, if you can, do large I/O from a single rank, MPI rank. Try not to append to the same file from multiple programs ever. And if you actually have to do I/O from multiple processes, doing it to separate files is a good idea as well. So it may be less convenient, but if you're doing I/O to separate files, that will probably be affecting completely independent file servers, and there will be much less interference. So these warnings about Lustre parameters with metadata and large I/O apply to global work and to Scratch on Orca, SAW, and Requin. Most of the other file systems we have are NFS, and NFS behaves somewhat differently from Lustre. So one of those file systems that's NFS is home. The home servers, there are several, and your home directory will be placed on one of them. They're very nice. They're actually high bandwidth, very high performance. We've done a good job in configuring them, but there are only a few of them for a lot of users. And it's easy to overcome their bandwidth capacity with lots of users doing I/O. So that's part of why we have a relatively small quota for home directories. It's important to note, though, that NFS has very, very nice caching properties. So if you're compiling, you should probably consider compiling like a large source tree in your home directory. Now, that may not be viable because of space, but the NFS servers that make up home are very good for compiling. Global work is Lustre. It's excellent. It's high bandwidth taken as an aggregate, but that aggregate is being split across hundreds of users. So there are hundreds of programs writing to global work at once, which means that it easily saturates its metadata capacity, but its file I/O is relatively scalable. Big file I/O is relatively scalable. Another interesting property of global work is that we can help you set up your files so that they are striped across multiple file servers. I guess I'll touch on this in a later slide. Scratch is basically like global work, except because it's not shared, not usually shared across systems, it tends to be less contended. Underlying file system is usually the same, Lustre, so it has many of the same properties, but Scratch is also usually on the cluster interconnect, and that means that the bandwidth to Scratch is potentially larger than the bandwidth to global work. It's important to remember that compute nodes have at least some local disk, and we tend not to make a big deal about this because it's sort of inconvenient to use them. But the best thing about local disks is that you're not sharing it with anyone, or at least you're not sharing it with very many other people. So they're not very big. They're not as fast. Well, if you really try, you can get faster I/O to global work or Scratch. So local disks are in the range of 100 megabytes per second. Global work and Scratch are both faster than that, even without striping. But the big advantage is that, if there are 300 some nodes in Orca, each of them has 100 megabyte per second disk. That's faster than the aggregate shared storage on Orca. The node local disk is usually just mounted as /temp or /local. We're perfectly happy to help you access these things. It's a little less convenient because you'd probably have to change your job script so that you copy data in and copy it out before your job finishes. The node local disks are wiped periodically, but in most cases that's a 2 or 4 week cycle. I think the best thing to do is to inquire with us if you think that this is a thing that you'd like to use, so that we can figure out the best way to do it. Here are some actual numbers. I was doing a bunch of testing, and it's interesting to do testing because when we get these systems, we do a lot of testing at acceptance time when we install the system, when it's new, and we're trying to decide whether to accept the whole system from the vendor. We don't do that much testing on an ongoing basis. We probably should, but here are some basic numbers. The best way to think about it is that on all of our Lustre systems, each file server, which Lustre calls an OSS, is about 150 megabytes per second. All of our Lustre systems have a number of these, so if you really had to scale your bandwidth, your disk bandwidth, you could scale it up to probably 6 is easy. So 6 times that bandwidth to a single file, to a single large file. It would depend on the node's interconnect bandwidth. It would depend on how big the file is, but probably 6 times that. So, close to a gigabyte per second is achievable pretty carefully with some tuning. The big issue with global work, though, is that because it's shared across many systems and many jobs are using it, chances are there will be some interference, so you'll rarely be able to talk to a single OSS exclusively, just your program. So you'll rarely see the full 150 megabytes per second for a long period of time. There's another issue, which is that the global work storage is, neither of them are at Waterloo, which is where Orca and SAW, our main clusters, are. It's a little bit hard to characterize how much that affects things. I guess you can think of the latency as increasing the chances of interference, just because for a node in Orca to write to one of the global works, it has to go over either a link to Guelph or a link to Western. And those links, although they're 10 gigabits, so 1 gigabyte per second, may be contended with epic traffic. It's important to be able to get your data in and out of SharkNet. For systems that are Unix-based, such as Mac OS and Linux, I really like SSHFS. At least I think that's usable on Mac OS. For sure, Linux systems can do SSHFS. What SSHFS allows you to do is simply mount your remote file systems from SharkNet on your desktop. This is, in my opinion, the ultimate in convenience. You can use file browsers. You can just treat them like normal local files. SSHFS is smart enough to do a certain amount of caching. It's still going over SSH, which is some overhead, but it's pretty good. Although you can connect to our login nodes to do file I/O, we often recommend that people use a single node called DTN. DTN has a very good network connection. It's actually located at Western, which is our primary networking center, I guess you'd say. And it has access, I believe, to certainly to all the homes, all the global works, and I think to most of the scratches as well, which is unusual. So normally scratches are shared only on the cluster where they're focused, but DTN acts as sort of a generic login node across all the clusters. You can't actually submit jobs from DTN, but from an I/O perspective, it's the place to go. DTN has globus grid FTP, and personally I like to use rsync. The nice thing about rsync is that it's incremental and it can always be restarted. I think we have help information on using both of those on our website. I'm going to skip to scheduling now. This is a thing. This section is filled out primarily based on confusions I think people have about how the scheduler works. So it's not obvious to someone who hasn't used a shared cluster before exactly what's going on and exactly what requests to the scheduler will result in the most satisfying jobs. So this is a bit of a review. A job requests CPU and memory resources, and for a specific set of time, a period of time. On GPU clusters, we sort of conflate the issue of CPU and GPU. But the real message is that it's sort of a block where the axes are CPUs, memory, and time. So you can think of it as sort of a three-dimensional cube. The scheduler is the only authority about where jobs run, and it knows what nodes are available and what resources the nodes bring. This means that your requests on any of these three axes will affect how your job is scheduled. And specifically, it will affect how soon the job is scheduled. The way to think of it is that if you want to avoid trouble with the scheduler, these are some things you should try to do. So don't request, well, request only the amount of memory that you think you need, and I'll talk about that. Request only the amount of CPUs, cores, that you think you need. Shorter jobs will, in general, get scheduled more quickly. And most of all, if you have work that's inherently serial, don't bundle it into an MPI program. That's sort of the anti-pattern for scheduling. It's useful to understand how the scheduler actually operates. So the scheduler has a cycle, and every cycle, all the jobs that are pending are examined to see which ones, examined in order of priority, descending priority, to see which ones can be started. The order normally depends on whether you're doing an NRAC or whether you're just doing a default allocation. NRAC jobs are configured so that they will basically always start sooner than normal jobs. NRAC does, however, have a fair share target. And the fair share target is really sort of like a resource quota. Unfortunately, it's always in just CPUs, CPU hours. So there's no fair share interpretation of memory usage or even type of job. It's just raw CPU usage. So NRAC jobs do have a fair share target. To decide whether a job should be scheduled, the owner of the job is evaluated to see whether they are near their their fair share target. And the fair share target just means that there's an amount of usage which the scheduler is aiming to provide to you. You can often exceed this, but if you're short of your fair share, you will have a small priority boost that will encourage the scheduler to run jobs until you reach your fair share. But really, the fair share and priority would be most relevant if all you had on a cluster was a set of serial jobs. And that's not the case on any of our clusters. So the complexity arises from when you have a mixture of jobs that require different types of resources. And the problem here is that our schedulers are, for the most part, greedy. That is, in every scheduler cycle, it examines all the startable jobs, and the ones that can be satisfied are started. There are a small number of jobs that are treated differently for each cluster, but the basic heuristic is greediness. And the consequence of this is that jobs that request the smallest set of resources will always start the soonest. So for instance, if you submit a serial job that uses the default memory request of 1 gigabyte on Orca, it will take longer to start than if you submit the same job that makes a request for 200 megabytes. Similarly, if you submit a job that requests 8 CPUs on the same node, the chances of 8 CPUs becoming available is basically exponentially less than the chance of 1 CPU becoming available. I mean, if you can sort of model this as, I guess, a Poisson process of resources becoming available. So if you're requesting twice the resources, it's actually a squared probability of your job starting. So this matters a lot for MPI jobs, where you might be tempted to request an MPI job run with a particular number of ranks per node and a particular number of nodes. Such a job is requesting a very specific layout, and it will take longer to start than a job that doesn't constrain how the scheduler lays out the ranks of the MPI process.